Okay, hope everybody had a good weekend, and thanks for coming at 9 o'clock in the morning. Bit cold outside, so hopefully can warm you up the next 2 hours. So what we're going to do, we're going to wrap up emulsion polymerization and introduce the concept of what a mini emulsion is. And after that, after those, I think it will take about 2 hours, maybe a bit less. Then we're going to move more towards physics. So we're going to look at how do things, small objects, move through liquids, and how can they keep stable, and all those type of things. So, but before that, we're going to continue or finishing off the last bit of emulsion polymerization. Okay, and I thought the best thing to do was just to check whether we understood the basic concepts of this. So there's a question up there, and the question is, which of these following statements is not correct? So the first one says that in the particle nucleation or formation stage, it doesn't matter how you call it, the number of empty micelles is dropping. B says the total number of growing latex particles throughout the particle formation stage always goes up. And C, when ammonium persulfate is used as initiator, the first propagation step of the persulfate radical generated takes place in the aqueous or water phase. And D, micelles are dynamic suprastructures and undergo continuous sorption. With sorption, I mean adsorption and desorption of amphiphilic soap molecules. So go for it. So 4 statements, and one of these statements is not correct. So is it that in particle nucleation the number of micelles is dropping? Is it that the total number of growing latex particles throughout formation stage always goes up? Or is it propagation in the water phase initially? Or is it that micelles undergo continuous absorption and desorption of soap molecules? Okay. Opinions are divided. About 55% says answer A is incorrect, and about 35% says that answer B is incorrect. And a few people say answer C, and nobody says answer D. Okay, so let's have a look at this. So the number of empty micelles, if there would be micellar nucleation, is dropping, right, throughout the particle formation stage. And the reason for that is you start to initiate in a water phase, so C is definitely correct. And then you grow a 1 mer, a 2 mer, 3 units of styrene, for example. And then you start to become amphiphilic, so you start to act like a soap molecule. And then if there are micelles, it will enter a micelle, and then it could polymerize there, which means the micelle is no longer classed as a micelle. So the total number of micelles will drop. So A is a correct statement. B, however, the total number of growing latex particles throughout the particle formation stage always go up. This was initially thought, but later on, when people looked a little bit more to, homogeneous nucleation, they saw that sometimes you could get coagulation at the very, very early stages of particle nucleation. And the reason was, if you think about it, you have one sulfate group, you start to form a polymer chain that collapses on itself. This thing will swell up a little bit, takes a bit more monomer. So basically, the surface area of this blobby object becomes larger, but it only has one sulfate group. That starts to become colloidally unstable, and a bunch of these then group together in order to get a better distribution or a higher charge density with respect to surface. So the incorrect answer, and what we asked for, is answer B in this particular case. Okay, let's move on. So we've seen particle nucleations. We started a little bit with particle growth. So now we're in the stage that once the particles are formed, we're going to assume that we're not going to make any extra particles. Sometimes this is not the case. Sometimes when you hit stage 2 in an emulsion polymerization where you're focusing on particles growing, sometimes there can still be ongoing nucleation or maybe even coagulation. So if coagulation events happen, the number of particles drop. And if nucleation continues to happen, for example, if you would have a very, very large radical flux, so you have a lot of oligomeric species being formed that are derived from a sulfate radical, for example, you could basically trigger an extra nucleation event. Or for example, if monomer starts to hydrolyze, you make, for example, methyl methacrylate then becomes methacrylic acid. You make ionic species in the water phase, and later on, at later stages, you can get a secondary crop of particles. But for simplicity, we're going to say after particle nucleation, after stage 1, we have a fixed number of particles. So no extra particles are being made, and then we're going to look at what happens then. So we saw at the end of last lecture that in the particle growth stage, when you look at the graph, it looks a bit strange because the rate of polymerization stays constant. And if we think that, you know, monomer gets consumed, obviously because monomer conversion goes up, then this is a little bit counterintuitive in first instance, because if you look at bulk kinetics, you would get rate coefficient of propagation times monomer concentration times radical concentration. If radical concentration is assumed to be constant, so you have a constant flux of radicals, then monomer concentration in a bulk polymerization would drop, which means the rate should drop. And in this particular case, the rate stays constant. So a question is, you know, what we could ask ourselves, what is the underlying reason for this? And that's what we're going to have a closer look at. So if you look at the equation there, the equation basically tells you that the first derivative of monomer conversion over time, which is an expression in a way for the rate of polymerization, it's related to that. It's not exactly the same, right? Because rates are expressed normally in concentrations. But in this particular case, conversion is, well, in every case, conversion is related to that. So you get Kp is the rate coefficient of propagation. Particles grow, which basically means the predominant amount of monomer gets consumed inside growing particles. So therefore, we need to know the monomer concentration inside the particles. Yeah, that's important. So that's CMP. And then N bar is a new kind of entity, which is the average number of radicals per particle. So this is a number. And because we have lots and lots of particles, so say 10 to the power 16, 10 to the power 20, you know, the average number is quite, it's kind of a nice number to handle, because if you would do this in moles, then you get weird numbers. So, and we multiply that then obviously with the total number of particles per liter. So the average number of radicals times the number of particles per liter. And then we have to divide by the number of Avogadro to get it back to molar. So that's what we do. And then in this particular case, we also divide by the analytical concentration of monomer we put into the system. The only reason why that's there is because on the left-hand side, we use conversion. Yeah, so then the equation matches. So this is a typical equation what holds for emulsion polymerization. And then there are a few things that you need to know, or you want to know. Kp, the rate coefficient of propagation, well, those things are known. They're measured by people that do post-initiation polymerization. You can look them up, what the values are, under a variety of conditions, temperatures. The concentration of monomer in the particle, that's something we need to have a closer look at. The total number of particles, well, if we know size and we can measure size and we know density, then we can figure out how many particles are there, so that's doable. And then obviously we can then calculate the average number of radicals per particle, because we know how much monomer we put into the system and the number of Avogadro is known as well. So the question now is, why does a particle take up monomer and how much does it take up and how does it do that? Well, the logical thing initially would be, we have large monomer droplets, we have a little bit of monomer in the water, so if the particle starts to polymerize, you could imagine that the concentration of monomer drops, and therefore you get transport from the water phase into the particle, and from the monomer droplet into the water phase. So that's the overall accepted way of how transport happens. A little bit slightly more controversial, but which you can also imagine, is that there could be a collision between a monomer droplet and a growing particle. and then immediately the growing particle can just take up as much monomer as it wants, and then it could be a reversible collision, and then, you know, go back into the continuous medium. So, but that's in not very many textbooks, but you could imagine that that plays a role as well. Okay, so let's have a question. What can we say about the swelling behavior? With the swelling behavior, I mean a particle taking up monomer. Yeah? So now, can a particle take up an infinite amount of monomer? So if I would subject it to a large excess of monomer, could it then just swell and swell and swell and swell and swell and become bigger and bigger and bigger and bigger? So what are the opinions on that one? So let's have a look. So press A if you think a particle can swell and swell and swell, and press B if you think that a particle cannot infinitely swell. So there's a discrete amount that can be taken up. Okay, so the majority of people agree that the particle can take up only a finite amount of monomer, which is good. So this could be a guess, or you know a little bit more than we've already talked about. So now the question is, why is this? Why would the particle only take up a discrete amount of monomer? So we can ask another question. We can say, okay, if there is a limit to how much I can take up, this limit might be set by the following. So you might say, okay, the interaction of the polymer chains with the monomer inside the particle plays a role. So if the monomer is a bad solvent for the polymer, so for example, acrylonitrile and polyacrylonitrile, acrylonitrile does not swell polyacrylonitrile very well, or in other words, polyacrylonitrile doesn't really dissolve in acrylonitrile. Is then swelling restricted? So is this something that's important, or is this something that you say, well, you know, it's a bit far-fetched, maybe this is not correct? So what do people think? So is the interaction between the polymer chains and the monomer, would that play a role in the swelling characteristics of latex particles? So about 95% of people say, well, I can imagine that this happens. Opinions are hovering a little bit. 10% says no, it doesn't really make a difference. So we should have a look at that. The answer is yes, it does play a role. You can imagine this, right? If a polymer molecule doesn't like a certain low molecular weight solvent or monomer, it will not really have the ability to take this up. It'll go like, well, you just stay in the water phase, I don't really care. Yeah? So, okay. So let's ask another question in relation to this. And that is, when a latex particle is cross-linked, so imagine now you have polymer chains into a particle and I link them all together, yeah, with cross-link. Well, for example, if I would use divinyl benzene, I have two vinyl groups then, and basically I can attach polymer chains towards each other. So in the end, if I could end up with like one molecule, one particle is one molecule, but obviously I can increase my cross-link density if I use more divinyl benzene in this particular case. So if that would be the case, would it matter how high this cross-link density is? So in other words, is swelling a function of the cross-link density? A higher cross-link density, would that lead to less monomer being taken up? Or do you think, well, no, it depends on the total amount of material that's there. So divinyl benzene is quite similar to styrene, and therefore cross-link density doesn't really play a role. So what do people think on that particular thing? So either it matters or it doesn't matter. Cross-link density matters or it doesn't matter. Okay, so about 75% says it matters, 80% says it matters, and 20% says no, it doesn't really play a role. So what you have to think about in this particular case, imagine it's well, it's almost like a fishing net, right? So if you've got it more tied up closely together, then the maximum amount that you can stretch it is less. Yeah? So if you swell and swell and swell and swell, the maximum geometry you can get is defined by how many cross-linking points you've got. If you would only have a few cross-linking points, you can expand way larger than if you have lots and lots and lots of cross-linking points, because you can't expand very much. And as a result of that, because your volume can't go up, you can't take up enough monomer in that particular case. Not as much as if you want to take up. So it restricts the amount you would like to take up. So A was the correct answer in this particular case. Okay, so let's have a look at the underlying science with respect to this. So this looks like an enormous equation, like I said last time, because I just whacked it on the board at the end. But let's have a closer look at this. So the question you can ask yourself, if styrene is a good solvent for polystyrene, yeah? So imagine I have a bit of polystyrene, and I put it in a jar, and I pour styrene over it. Then what you'll end up with is that the polystyrene dissolves, and you get a dilute polymer solution. And you could, in a way, you could infinitely dilute that polymer, because you can pour in more styrene, and it's going to be fine. It's not going to say, well, you know, I don't want to have more styrene. You just get a more dilute concentration of polymer in solvent, and the solvent in this case would be the monomer. Yeah. So the underlying question now is, why does this not happen in case of particles? And so that's something people looked at. And the answer, the initial answer, lies in the Morton, Kaiserman and Altier equation, the MKA equation, which is combined with another equation, the Flory-Rayner expression, and the total of that is displayed in this large function under there. But now we have to digest this function a little bit. Yeah. So let's first look at the right-hand side of this equation. So I see I have got an ln 1 minus well, volumetric term in there, and that volumetric term is related to the volume fraction of polymer. So 1 minus the volume fraction of polymer is in a way the same as the volume fraction of the monomer. And then I've got plus 1 minus 1 over J2. And J2 in this particular case means the number degree of polymerization. So I'm going to assume that monomer takes up 1 unit. And obviously if I have a polymer that's composed out of multiple monomers, then the number degree of polymerization kind of reflects J2, yeah, size-wise. So those two terms are the entropic terms of mixing. So we've seen that a little bit before. And entropy always promotes mixing. If entropy was the only thing out there, everything would mix. Obviously, that's not the case, right? Oil and water don't mix. If you have two materials, some things mix better than other things. And as a result of that, there is a correction term. And this correction term in polymer science, but also in other disciplines, is described by the Flory-Huggins theory. And the Flory-Huggins theory gives you the third term in this case, which is the Flory-Huggins interaction parameter times the volume fraction of the polymer to the power 2. And the Flory-Huggins interaction parameter is a measure for how well stuff mixes. So you can actually do some experiments and you say, okay, if I know my entropic terms, which are basically only defined by the length of my polymer and the volume fraction, so that's easy to measure, the interaction parameter rules out of that. So for a system, polystyrene to styrene, you can look up what this parameter should be. So that's the first 3 bits. And then we have the last bit in this equation is a correction term. And this correction term is the Flory-Rayner theory and basically deals with crosslink density. V1 in this particular case is the molar volume of the solvent. In this case, the same as the, the molar volume of the monomer. And it's multiplied by the density of the polymer. And then it's divided by the molecular weight between cross-linking points. So if there are no cross-linking points, that term basically goes up to infinity, yeah? And it just completely disappears. So this term only is important when you use a cross-linking agent. For example, if you would use divinyl benzene in the polymerization of styrene, because basically you reduce the distance between 2 units of divinyl benzene if you use more, yeah? And then the correction term between brackets then is only a function of the volume fraction of polymer used. So you have in a way, 3 terms here. The first 2 there are the entropic contribution towards mixing. The one in the middle is the Florey-Huggins interaction parameter. So say something about the enthalpic contributions. So is there a positive interaction between the polymer and the monomer, or a negative interaction? Yeah, so that term is the only term that can account for that objects don't mix. And then the last term is almost like a geometric restriction. It's related only to the cross-link density, and it's only important then obviously if you use a cross-linking agent. If you don't use a cross-linking agent, MC goes to infinity, which means that term cancels out. So that's the right-hand side of the equation, yeah? Now the left-hand side, there's a little bit what you might recognize, which we saw in the first, I think the first or the second lecture. There's a Laplace pressure term in there. So this only holds for a sphere, yeah? 2 times the interfacial tension divided by the radius of the particle that is swelling. So that term, in other words, or if you would derive that term, it's basically the Gibbs-Thomson relationship. And what it basically says is like, if I would swell a particle, I will start to make more interface. And if I start to make more interface, that's work, and that's not a good idea, because it increases the energy, and you want to decrease the energy. So the interfacial tension will restrict how well a particle can swell. As a matter of fact, in this particular case, if you would look at polystyrene and styrene, so don't use any cross-link density, the right-hand side effectively, if that was only there and you wouldn't have a particle, you could infinitely dilute. The left-hand side would restrict that. So the restriction, the important restriction in that particular case would be the increase in interfacial tension. Because, well, sorry, not in interfacial tension, the increase in interfacial energy. Because the radius of the particle would go up. Yeah, and tension times area would be the interfacial energy. So that restricts the maximum swellability. So there will be a finite amount of monomer that could be taken up into a particle. And you could measure that, for example. You could have a bunch of latex particles, expose it to a large excess of monomer, of solvent. You stir them up, let it come to thermodynamic equilibrium, and then you measure how much is in there. So you could, for example, you could separate the monomer from the swollen particles by centrifugation, for example. And then you can measure how much monomer is in there, either by gravimetry, as in blow everything up and see how much solids you've got left, or for example, by density measurements. Yeah? Now, this theory works relatively well. However, there are some people that say, well, it's not perfect, and sometimes some corrections need to be made. And as a result of that, I put one of these question marks on the equation as well. And you can see that Klaus Tower, for example, said, okay, in addition to the contribution of this interfacial free energy, I also have to do something with attractive forces between polymer chains. So you could argue that that term has to be in the interaction parameter, in the which is a constant, to this equation. So it's like a fitting factor almost. Yeah. You could also argue, which is not displayed here, that okay, imagine I have a sphere with 100 sulfate groups on it, and these sulfate groups are derived from my initiator end groups, and they have a certain interfacial tension, yeah, and the interfacial tension is not very high because these sulfate groups lower the tension between the hydrophobic particle and the water. But if I now swell, I move these groups further apart from each other. So you could argue that interfacial tension in this case is not a constant, but is a function of the swelling of the droplet as well. Which means then you have to, you know, make it more complex by writing interfacial tension as a function of the radius of the particle. Anyway, so let's just have a look at, you know, how this large equation, how that works. So here is some real data. So in figure 1, you see the diameter of the swelling particle as a function displayed of the volume fraction inside the particle of the monomer. So the points are real data points, and the lines are data fitted with the MKA equation, with the relatively simple Morton, Kaiserman, and Altier equation. And in order to solve this, you gotta put a number of parameters in there, which you can read. It's a bit difficult to read. The letters are quite small, but if you print the slides out, you can see it. So they basically, you have to know what the molar volume of the monomer is, and in this case, that would be 9.36 millimoles per cubic centimeter. The temperature, in this case, it was 25 degrees Celsius. You need to know the molecular weight of polystyrene. So it's quite common that in an emulsion polymerization with a very large flux of radicals, you get very high molecular weights. So you could basically say, well, J2 goes towards infinity, and that's what they've assumed here. Crosslink density in this particular case is 0, so the MC goes to infinity. And then you have to have an estimate roughly what this interfacial tension is. So they plotted the data with different values of that, and then you get those lines. So it's a relatively okay fit. Yeah. So interesting to see is that, you know, for a latex that has a charge density, so charge density, I mean the number of charges spread out per square meter. Yeah. So if you have a lot, then obviously that number is higher. If you have a little amount of charges on the surface, then it's less. So you see that for quite a charged latex, minus 19 microsiemens per square centimeter, those are the black data points. You can see that if you increase the particle size, you can swell quite a lot. So you can go up to almost 0.8, 80%, 80 volume percent of monomer would go inside the particle. Now, we talked a little bit about, you know, what if this latex is less charged? If it's less charged, would mean the surface tension is higher. So the second or the third set of data has got a lower surface charge density, so minus 8.6 microcoulomb per square centimeter and minus 7.5 microcoulomb per square centimeters. And you can clearly see you can swell less. The reason for that is that the interfacial tension is higher. Yeah, so you take up less monomer in that particular case. Now, the data on the right is just the data from Klaus Tauer fitted with this modified equation. You know, it fits slightly better than the one on the left, but there's no major differences. So in other words, the MKA equation gives you quite a good description of what happens in these type of systems. Okay. So we've dealt with how much monomer can go into a particle, and we've seen that, you know, for relatively highly charged systems or for systems that are stabilized with surfactants, you can get up to like 80% of monomer in there, and then you have 20% polymer. So you have a certain amount of monomer in there. So typically for a polystyrene polymerization, you'll end up with about 5 to 5.5 moles per liter is the concentration of monomer inside the particle. And that's what you need to put in that equation to fit your conversion data. So we talked about how this monomer would basically enter the particle. So your monomer goes from your monomer droplet through the water phase into the particle. That's the main way of transport. So you could think about this, is this actually fast enough? Because if I do a polymerization inside the particle, and if my polymerization is really fast, monomer has to enter the particle at a speed greater than its consumption. But if it doesn't do that, that basically means that I will have a shortage. So if my supply chain is not fast enough, I will run out of monomer that's polymerizing inside my particle. So what's really important is how fast does this monomer go through the water phase, and how fast does it enter a particle. Now, the rate of polymerization, so if I imagine I've got one particle, only one particle, and if I look at that one particle, the rate of polymerization in that one particle is Kp times the concentration of monomer in the particle, which we could measure or calculate with the equation we did before, times the average number of radicals per particle. And then the other event is entry of monomer molecules inside the particle. Now, think of a monomer molecule as a ping pong ball, and think of a particle as a larger ping pong ball. In order for these things to enter, they have to collide with each other. Yeah? So a very, very small ping pong ball has to collide with a very large one, and then you're basically back to collision theory. So hopefully in kinetics, in year 1 or in year 2, or maybe even in year 3, you might have heard of the Smoluchowski collision theory, which determines how fast two objects collide with each other. If there is no barrier for this collision, so there's no reversible collision in this case, that's the case in this case. We assume if a monomer molecule hits the particle, it gets taken up. Yeah? So we use Smoluchowski theory for that. We will come back to this in case you haven't had it, or in case you've forgotten this, when we start to talk about particle self-assembly and particle coagulating with each other. But for now, the rate of monomer entry is described by 4 times pi times the diffusion coefficient of the monomer in the water. How fast does it go through the water phase? Times the number of Avogadro, times the radius of the particle, times the concentration of the monomer in the water phase. So these two things are those two events. You have one side, you have the rate of polymerization, the other side, you have the rate of monomer uptake. Yeah? So you can see that, the rate of entry there is a function of the diffusion coefficient of this monomer, but more importantly, or equally importantly, it's a function of the concentration of the monomer in the water phase. So if you would have a really hydrophobic monomer, or a really hydrophobic solvent, then that concentration would be very little, which means that the rate of entry would be very little, which means that there is a likelihood that the rate of entry would be less than the rate of polymerization, which means I don't get enough supply, which means I end up with a diffusion-controlled reaction. Yeah? So you could artificially induce this by not chucking in all your monomer from the start at the same time, by feeding it with a pump really slowly. Yeah? We then speak of starved conditions. So if you feed in the monomer at a rate slower than it's consumed, you basically lower all the concentrations. That's called starved conditions. And sometimes the last bit is very interesting because you can make morphological structures that are kinetically frozen, which you normally couldn't make. So you could make a core shell particle, for example. So you can have a polystyrene particle with a Teflon shell, I'll fluorinate a shell around it. And normally, you wouldn't be able to do that. So there's some playing tricks with respect to that. Okay. Now, here's an exercise question, which I want you to spend some time on. So when we use monomer, which is sparingly soluble in water, the reaction can become diffusion controlled because entry becomes slower than the rate of polymerization. So knowing these numbers here, what is the water solubility of monomer X at which this becomes critical? So I have the radius of the swelling particle, the average number of the radicals per particle, the rate coefficient of propagation is given, monomer concentration is given, temperature is given, number of Avogadro is given, and the diffusion coefficient of the monomer through the water is given. So write these numbers down for a sec. Yeah. And then I'll go back to the previous slide, and then you can work it out.